Hello, everyone, and welcome to the Sunshine Coast Ocean Festival. This is day 3 of the festival and our 2026 Nemo Talk series. We're so glad you could be with us today. I'm Suzanne Sanger, the Executive Director of the Sunshine Coast Conservation Association, and I'm joining today from Chequelp, Gibsons, at Katsimhow Sound on the ancestral and unceded territory of the Squamish Nation. The SCCA works across the full length of the Sunshine Coast, from Howe Sound to Hamathko, in the territories of the Squamish, Shishak, Tliamin, Klahoose, and Homolko First Nations. These nations have lived in relationship with these lands and waters since time immemorial, developing the knowledge, practices, and governance systems to keep our coastal forests and rivers and ocean ecosystems healthy and abundant. Their knowledge, their work endures and is actively guiding stewardship and restoration work happening across the coast right now. The SCCA is really fortunate to be able to work in collaboration and participate with the First Nations on the Lower Sunshine Coast to do some of this work. We're deeply grateful for their ongoing care of this place, and we really draw deep inspiration for this project, for this program, and for all of our work from the Indigenous leadership here in our communities. And we're committed to supporting that leadership work together. The SCCA partners up with Rhizome Up Media for the Sunshine Coast Ocean Festival, and we're really stoked this year to have an amazing week full of in-person and online films, place-based science and educational activities and resources, our Oceans Day celebration on June 14th, filled with all kinds of really fun activities and ice cream, and of course, our fabulous Nemo Talk series. This year's festival has also been made possible through the generous support of the District of Sechelt, Sunshine Coast Credit Union, Ocean Week Canada, Sitka Foundation, BC government, and the federal government funding programs. The goal of the Ocean Festival is to learn, inspire, engage, and connect people with projects and programs and knowledge to encourage meaningful action to steward our oceans. So we are very thrilled to have to host Greig Oldford today from the Department of Fisheries and Oceans Canada to share with us about hindcasting the Salish Sea. Greig is a marine ecosystem scientist focused on understanding how ocean conditions shape food webs, fish populations, and the future of coastal ecosystems. He leads integrated ecosystem modeling work with DFO and is completing a PhD at the University of British Columbia, where his research links ocean physics, plankton dynamics, and fish ecology in the Salish Sea. His work uses computer models, long-term monitoring data, and ecological theory to reconstruct how marine ecosystems have changed over decades and to help inform better decisions for fisheries, conservation, and ocean management. Passionate about making complex science useful and understandable, Greig works at the intersection of research, policy, and public communication to help communities like ours see the ocean as a connected, living system. I'm going to pass it over to you, Greig, to introduce your talk, share your screen, and take it away.
Well, thank you very much. It's a pleasure to be here. Thanks for the invite. I'm excited to share with you some of the work that I am doing with partners at UBC and at DFO. I'm going to try and share the right screen here with you. See if this works. Okay, just a sec. Bear with me while I get this reversed. Okay, let me know if you can see my slide.
I'm not seeing your
Not
share
quite
screen.
yet.
Okay.
I think you
Try one
unshared.
more time. And how about now?
We're working on it. Yeah, there we go. Yes,
Great.
perfect.
Okay. Thanks very much. So, what can ocean ecosystem simulations tell us about impacts of long-term environmental changes unfolding around us here in the Strait of Georgia? Um, this is mainly a topic that I work on as an ecosystem modeler, a PhD student at UBC, and I've had the privilege of being involved in this work for some time, supported by Fisheries and Oceans Canada, UBC, the Pacific Salmon Foundation, and various funding sources, including MITEX and NSERC. The topic of our simulation work is the Salish Sea. It's a unusually diverse area. It's in terms of marine life and globally speaking, there have been clear physical and ecological changes documented over recent decades. And these changes affect many marine species and habitats of cultural and economic importance. And the Salish Sea is important for many species of cultural and economic and social interest, but a few of them here are particularly iconic. That includes Pacific herring and five species of Pacific salmon. Pacific herring and salmon, just the salmon complex writ large, are good examples to draw on because they use the Strait of Georgia. They particularly rely on the Strait of Georgia at a particularly vulnerable time in their life history. But something strange seems to have happened in the early 1980s to two iconic species, the coho and chinook in particular. Their survival rates fell steeply during the period that they spend in the strait as juveniles. The two species spend more time in the strait as juveniles when they enter the marine environment from fresh water, and nobody really knows why this happens. And why did it happen when it happened? And are environmental changes to blame, or is it potentially something else? So this remains a mystery, though there are some clues and many hypotheses have been investigated by scientists over the years. One hypothesis is that ocean conditions changed, and this in some way has led to the poor survival that we've been observing. But a problem is that many of these changes in survival happened over 40 years ago. So, how can we actually know what environmental conditions a fish in the Strait of Georgia experienced many decades ago? We do have some measurements. We have some measurements that were taken, but nearly all of them are taken in more recent years. We have regular measurements from one location back to 1980, even the 1960s, but it's not very clear whether that one location is really representative of other locations in the strait. And furthermore, environmental conditions is a very broad term. So do we mean temperature, salinity, or what depth? What depth do we mean? And where? Where in the strait? So these changes are part of a group of broader climate-driven shifts in the coastal ocean conditions and regional atmospheric conditions. These changes have impacted the properties of the fresh water entering the strait. About 75% of the fresh water enters the strait from the Fraser River. It's just a huge amount of water. It's something like 115 billion cubic meters per year. So the rainfall patterns, snow melt, river runoff patterns, they all influence stratification, nutrient supply, and the timing of the spring conditions in the strait. And several studies have documented that changes in precipitation and runoff are affecting the strait, and that it's notable that spring conditions are a critical period for fish and many other marine organisms. Productivity in the strait is highly seasonal, and plankton productivity especially peaks in the spring. And that provides food for juvenile fish like Pacific salmon and herring. But our problem is that the measurements that we have on the scale we want are just too sparse. There's just too many gaps. We do have tens of thousands of observations. And here I'm showing a map of the Salish Sea with the Sunshine Coast roughly in the center. The especially in decades past, though, even though we have tens of thousands of samples taken throughout the strait, there are too many gaps at the local scale, and those are scales that are particularly relevant for juvenile fish. One location does have sampling that extends back to the 1960s, as I mentioned, and samples were taken on a weekly basis at this one station. That's the star in the center of this map here, and that station's called Nanus. When we look at the raw data that we observed at Nanus, you can see that it shows something really remarkable. The entire water column's temperature shifted in the late 1970s, roughly speaking. So you can see on this plot where depth is on the y-axis, the shallower waters are on the top of this plot, and the colors represent water temperature overall depths. This pattern was observed at Nanu Station, and it really leaps out as a potentially big shift in water temperatures. Many species can be affected by what seem to be small temperature shifts, but it really isn't clear whether this pattern really holds for the rest of the Strait of Georgia and the broader Salish Sea. Many other areas are important for juvenile fish than this one location. So that's where the computer simulations that I wanted to talk about today, they can help. So just like the atmosphere, simulations can be developed for the ocean. These simulations can be short-term, like weather forecasts, and often are, or they can be long-term. We generally call these projections. Ocean simulations, they use first principles of physics and chemistry to make predictions, and they perform remarkably well. It's absolutely incredible given the complexity of the system that they do work. But the same foundational principles are what is used to enable many technologies that we're familiar with. So planes probably wouldn't fly very well without the simulators that are used to test the design of the airplanes. And they use some of the same equations as the ocean modelers use for fluid dynamics and that sort of thing. And similarly, the reasons our phones and laptops don't immediately overheat is that these types of simulations using the basic physical principles, they do work. So physicists and software engineers and chemists and biological oceanographers, they develop ocean simulations that are used operationally. We look at what was available for these models, or we looked at what was available for our area, and we found that what was available for the Strait of Georgia and for the Sunshine Coast was either very short-term oriented or very coarse in terms of spatial scale. There was one model developed at UBC that seemed possibly feasible to use as a hindcast back to 1980. And a hindcast means a backward-looking simulation. So we're looking backwards through time. The team up at UBC, it's led by Professor Susan Allen. They used a model called the NEMO model. So it's a good fit for today's talk. The NEMO model was being used for forecasting, so short-term projections. And one of the reasons the model that they had up at UBC wasn't suitable for long hindcasts, long simulations, is because it's very, very computationally intensive. To run the model, which is called Salish Sea cast, for a 40-year simulation like we used, it just would be totally infeasible to do that. It would occupy resources on one of the biggest supercomputer clusters in Canada for weeks, maybe months to do that. And it might have even had to be run more than once. So what we did is we decided that we needed to simplify their model. Instead of 500 meters, we reduced the resolution to 1.5 kilometers in terms of the horizontal resolution or grid size that was used. And we simplified it by using a simpler version of other components in the model, and we removed some components too. So we just kept the basics. It's basically a bare bones version of the model that was available up at UBC and DFO. Um, this wasn't a small task. It takes a pretty good team with specialties to make it happen. But even a bigger task than retrofitting this model for this purpose was confronting the model with data to ensure that its predictions aren't too different from the measurements that we have. And that step is called model evaluation. That step involved digging into millions of data points collected over the years. And these data were collected by many different institutions and come in many different formats. So eventually, through collaboration and many gallons of coffee, we got there. And it was an exciting moment when the simulation finished running on this high performance computing cluster, and we got a first look at the results. The I should say I'd like to plug the Digital Resource Alliance of Canada, which is a partnership between universities and government to provide high performance computing to researchers like myself. So the results of the evaluation were initially very good in many respects. There are some results I've shown here. There are a couple of areas where the model didn't match the data, and that was especially the case in the upper part of the water column, especially in certain seasons and certain areas. So I can explain what you're seeing here. We're seeing on the left-hand side, the leftmost column, or panels A and D, we're seeing the observations and then of salinity over depth. So we see depth on the y-axis, the vertical axis implies depth. And then the x-axis is labeled by month. So throughout all seasons, we see the typical salinity measurements and the typical temperature measurements over the course of the year. In January and February, we see water temperatures that are typically 7, 8, or maybe 9 degrees throughout the water column. And in the summer, on average, we get temperatures that are higher, that are obviously closer to 20, but usually between 15 and 20. And the model is generally pretty good at predicting this same pattern. But on the right-hand side, you can see the model minus the observations. In the top panel, the numbers and the coloring denote whether the model was too fresh or too salty. And in the bottom right panel, it denotes whether the model was too warm or too cold, and if so, by how many degrees on average. And so from this, we can see the model has error. It's not perfect, but the bounds on the error over a season or month across all years for which we have data are typically less than 1 degree centigrade and less than 2 or 3 uh, salinity units. So overall, very good, but we do see like a red area in the center of panel F, especially in the spring, that implies that there's a error or bias in the model that's near the surface. So it's predicting the surface water temperature is a little too hot. So we had a problem on our hands there. Um, so what we did was we had to do a bit of detective work to track down the main source of that error. We investigated a bunch of hypotheses, but eventually we tracked down a single source of bias at the boundary near the mouth of the Juan de Fuca Strait. That's west of Victoria, and that's the boundary of our model. So what was happening was the boundary is where our model ends, and the ocean conditions at that point were coming from a different data sources, and those sources had issues. So once we accounted for that error, we adjusted, we did something called a bias correction. We found much improved results in our model outputs. They improved remarkably, especially with respect to ocean temperatures, which is what I'm showing here on the screen. It was pretty exciting because the model's skill, that's how far off the predictions are from the measurements, is after the bias correction is definitely within a margin of acceptable error for the applications we're talking about. Um, so yeah, here we see in the dashed lines um, again we see depth on the y-axis, and then temperature in the left column, salinity in the center column, and then just the number of observations we're using in the right column of the center panel. We see that the initial model had an error or was predicting temperature that was too warm over depths in the dashed black line, but the dashed red line shows the model after being corrected. So we're getting very close to what was observed. We still have, again, biases in salinity and temperature, but typically they're within less, the error, the amount that the model's off was within a couple or half a degree or so in terms of water temperature. And then there's a target plot, which is a bit difficult to interpret, except that you want the model's results, you want these figures on the right-hand side, the icons to be at the center. So the gray is before we did bias correction, and the red is after. And we see that the bias started to approach zero, which was very good. Even though the variability is a little bit off still, it's generally speaking very useful for substituting these outputs for observations for many applications. So once we accounted for and corrected the bias as best we could, then we reran the model and the results were improved. And then we couldn't help but look at what does it predict in terms of the trend in temperature at that one location. So that's the Nanu station that I mentioned in the center of the Strait of Georgia. We have looked at that here and displayed the results in this plot. We've got observations as the black line and the model, the HOTSSea model outputs in red. And generally speaking, it's again, it's capturing these trends in water temperatures very well. And we're quite pleased with that. Typically within a couple of uh, basis points or a couple of tenths of degrees from the actual observations. We do miss the cold period between 1970 and 1980, and that's simply because we don't have the resources we need in order to extend the model back further. But it is a priority in the future. So looking further into the trends, we're again looking at depth, the model's prediction of temperature over depth, and the observations of temperature over depth. The model is in red and the observations are in black. But here we've divided up by season. So on the far right, we actually see the annual pattern on average. We see that annually speaking, over these 40 years, these surface waters are warming faster than the deep water, which is to be expected because the ocean water is being influenced by the atmospheric conditions. But the main takeaway here is that seasonally, if you break down these trends, certain seasons are experiencing greater warming trends than other seasons. In fact, there's very little of a warming trend detectable in the winter season. But in summer, especially near the surface, we can see from the model results and the observations at this one station that the surface waters in the summer are warming much faster. On average, over 40 years, the trend is roughly 0.25 or zero point 0.3 degrees per decade, which, relatively speaking, is very fast for a large body of water like this. Um, we we then took our model results and we asked, what does it say elsewhere in the strait other than at the Nanu station? And we found here that it looks like again, the waters near the surface in the top 30 meters are warming, but we immediately see that there's a spatial trend. The spatial pattern is not uniform. It's clear that most of the warming trend is concentrated within certain areas and within certain seasons. And again, the summer season is experiencing a particularly acute warming throughout the strait. The waters are increasingly stratified when they warm, so that means the waters aren't being mixed as intensely, and this can lead to many of the knock-on changes. We don't see the same warming trend at all in the spring in this map. So we can see the spring is showing a gray hatched pattern in panel B here, which really is just to translate that to what it means, it's just no pattern or no trend detected. But what is happening in the spring appears to be that things are getting more variable, they're getting more unpredictable. And the increasing variability increases the chances that there's a mismatch between the timing of juvenile fish entering the Strait of Georgia and the timing of their prey. And what's also notable in these spatial maps of the Strait of Georgia, where the Sunshine Coast again is located roughly in the center, um, is that is the spatial pattern of warming is generally more strong in fjords and bays in shallow areas. Again, it's to be expected, but we didn't know that without for sure without running the model. There's still some uncertainty, but it revealed for the first time that um, the eastern side of the northern Strait of Georgia in the winter does appear to be warming, but the rest of the strait isn't feeling those same effects. And there are many explanations for this, why this would be, but we've barely scratched the surface. We're just looking at the 0-30 meter depth band. We have just broken it down by season. We can break it down in other ways as well. And we also see that what really jumps out too is the fall. The fall is just consistently warming throughout the domain and more or less with local variations. And so it opens up some questions. Is what's happening the season, is the summer season essentially being extended on average further into the fall? Are there other changes afoot that we don't know about yet? And so overall, I think the takeaway is that the long-term trends aren't expected to be unfolding in a uniform way, spatially or temporally. Seasons are going to be experiencing different effects. And I think many of us have observed some of those effects already, or at least felt them. But there are several caveats I should mention. Like, for example, if I draw your attention to Jervis Inlet, you can see that the fjord is warming faster than other areas, generally speaking. And that's to be expected since it's more inland. It's more impacted by atmospheric temperatures and runoff than deeper waters of the Central Strait. But you'll recall we had to make some compromises. The model represents a bare bones version of another model. One of these compromises is likely very apparent for the audience today. So you'll notice that Seashell Inlet is entirely missing. That's because we had to use 1.5 kilometer resolution. The map becomes so simplified that if we essentially lose the ability to incorporate narrower channels and fjords. It's undoubtedly affecting the model skill, and in these fjords, we generally have fewer data to compare against. So it's harder to detect potential issues and address them. Nonetheless, we should expect fjords, bays, shallow areas to warm faster, and it's just because they're more generally affected by physical stratification and decreased mixing than our open waters are. So just to rehash, why does this matter? The NEMO model helps us fill a gap in patchy observations, helps us understand the past. And although there are many ways that simulations like this can be improved and will be improved, the results that we have here represent an important advancement. It is just generally harder to model nearshore areas, especially areas like the Salish Sea and the Strait of Georgia. And this model fills a gap with that respect. And then there are patterns that are very intriguing. And I didn't talk today about salinity, which is not very much anyway, which is also very important for many species. Salinity is very important for kelp and eelgrass, for example. The simulation provides useful results for the first time, and then it gets us closer to understanding how and what conditions a fish would have experienced in 1980 versus what they experience today. And the results of our hot sea model are already being used by other researchers investigating how we can reduce the risk to fisheries, to aquaculture, to habitats, and iconic species that live here. So what's next is we'd like to increase the resolution of the model. So we'd like to resolve areas that, like Seashell Inlet, that are less than 1.5 kilometers in width. We'd like to extend back further, ideally. We'd also like to look forward into the future more. And because if we can credibly simulate the past, we should be able to improve predictions about the future. That's a major aim. But today I'd like to highlight one of the applications that we really want to do and have been doing, actually. We're very close to finishing something. That is to close the loop. There's sort of still a so what question. So waters are warming, and we know that extreme weather or more variable weather events are increasing, but we ultimately want to know what this likely means for juvenile fish. We know that fish are influenced by environmental conditions like temperature and salinity, but there are many pathways of effects. Some fish and some stages of fish are acutely sensitive to what seem like small changes, but I'll focus here on food. So how might the prey available to juvenile fish, like coho and Chinook salmon, change since 1980? To get at this question, we're turning to another simulation to pair up with our NEMO-HOTSSea model that you heard about today. So that model is an ecosystem simulation. It involves many of the same steps that we just went through for NEMO-HOTSSea. That is, we develop the model, we run the model, we evaluate the model, and then we analyze the results after that to understand what it's telling us. This simulation is called the Strait of Georgia Ecosystem Model of Lower Trophic Levels. It's a mouthful, so we just call it SOGEM LTL. The lower trophic levels refers to the base of the food web. That's basically speaking plankton. So phytoplankton are tiny plants, essentially. The community of phytoplankton is amazingly complex, and the animals that consume phytoplankton are referred to as zooplankton. And there are also other important ecological groups like bacteria, algae, detritus, even viruses and fungi. But for now, we've constructed a model that is bare bones in many ways, similar to the NEMO model, just to do a first pass. Even though it's simple, it's still pretty complex. It has 22 ecological functional groups. This illustration gives you an idea of basically how it's set up. We use the physics from the NEMO-HOTSSea model I told you about to force this model. And at this point, we've evaluated the results of this model, but we've only done a very preliminary check on the trends and what the model is telling us. I can share a little bit. It's very promising. On the left-hand side, we see zooplankton seasonal community dynamics. So the model is making predictions that we've represented in blue on a monthly basis for diatoms, for dinoflagellates, nanophytoplankton, picophytoplankton. These are sizes of phytoplankton and general classes of phytoplankton, many of which are components of harmful algal blooms. Then we did look at long-term anomalies predicted by the model in terms of crustacean zooplankton. These are generally good prey for juvenile fish. And then finally, and the predictions are fairly close to the limited observations that we have. On the right-hand side, we have a plot of the phytoplankton bloom timing, the spring bloom timing. So it's representative of the point in the spring when winter transitions to spring. The model again is predicting the day of the year in blue, and we're comparing it against some satellite data that we have for 2003 till 2016. And generally, we're pretty pleased with the ability of the model to predict what we observe. So just to wrap up, environmental conditions in the ocean, they generally affect marine life of the ocean, and there are long-term changes that are affecting the Strait of Georgia and the broader Salish Sea. These changes are affecting many species, and they're expected to be responsible for some proportion of the mortality experienced by Pacific salmon and other species like Pacific herring, especially coho and chinook, though, which rear for longer in the Salish Sea than other Pacific salmon. And we expect the effects of long-term changes to ocean and atmospheric conditions, that is climate change, to be more pronounced in inland seas like the Salish Sea. So through using big simulations, we were able to address some gaps in historical observations. And when we compared against the historical observations, the model did very well. The trends unfolding within the strait are not uniform. This is what the model revealed to us. And to see different rates of change in different areas and seasons is not a surprise, but it is interesting to look at how these exactly where the trends are different. These changes are likely to affect the availability of high quality food for fish, and we hope by refining our understanding of the prey impacts by building upon our physics simulation, we're able to learn more about what has changed in important ways and impacted juvenile fish. So far, so good. Ultimately, how can we use this knowledge? How it's basically up to us. Uh, and likely it's highly specific to your concerns. But broadly, I think we can all do our part to reduce impacts. We can take measures to help protect and restore important habitat and be responsible stewards of our oceans as best we can. So again, thank you very much for the invite to speak to you today. Um, this project and all this work summarized today involves a great many people. So I'd like to get an opportunity just to say thank you to them. And I welcome any questions. If you'd like to reach out and talk after this, that would be great.
Greg, thank you so much. That was a very full presentation. There's so much information in there. I'm still sort of like it's all processing, percolating. It's cool to see how many partners you've got. That the government projects are working with all the universities. And then that last sort of added piece at the end of this whole other model that is, adding in the ecological side of it, not just the temperature and the salinity piece. It's amazing and fascinating to see as well how, through testing and um, you can figure out where you're missing data to actually, see how accurate your model is. And this is, when we do these talks, a big takeaway is, what can we do as the public? How can we help? The whole time you were talking, I was like, wondering what Maggie posted in the chat for her question, which was, are you using this data? Are you using, so I feel like a big takeaway is what data is missing? Where can the public contribute to this project? So that's just sort of some of the first thoughts that are rolling around in my head. We do have a couple of questions. Are you ready to take some questions?
Sure, yeah, happy
Okay.
to.
So this is Maggie. She was asking, is the data from the forage fish egg sampling also included? Water temperature and eggs are found seasonally. So are you guys taking those data?
Well, forage fish sampling, I guess it would depend on specifics. So for example, the surveys that are done annually, dive surveys or surface visual surveys of egg deposition from Pacific herring, absolutely. Yeah,
Mhm.
we have those. They're a very valuable data set. They're spatial. They extend back an unusual for ecological time series. We're really quite limited. We often have only dozen years or so, or something like that. Those data are particularly valuable. Yeah, and so we will use them in the spatial in one of the versions of our ecosystem models to help validate the model's predictions and also just to help it make be more realistic. So we can also force the model in some ways too. So yeah, those data are particularly valuable.
I'm going to just carry this one a little bit deeper because we collect data at streams through like stream keepers work and through restoration projects, temperature and that kind of stuff in the creeks, and we submit it all through the Pacific Salmon Foundation now. And but the forage fish the forage fish sampling work that we're involved in the SCCA, it's not about herring, it's about surf smelt and sand lands. And
Mm.
so I know that the funding for this programming has kind of come to an end, and there was all this beautiful work that took place over the last couple of maybe like 10, 15 years, including in Seashelt Inlet, that drove restoration projects. And I don't know where all that data is going to end up. So this is, just planting egg seeds, right? Going like, and also wondering like, are there spots where your team is dying to have consistent data and groups like ours or other groups around the Salish Sea might be able to contribute?
Well, the some of the most important ecological data, the observations of um, egg deposition, species distribution, species abundances, habitat extents and change over time. It's related to forage fish generally, just because of the nature of the system. It's basically well, referred to as a wasp waste system, which one of your previous talks was all about. The species of particular importance, of course, like Pacific herring, as I mentioned, surf smelt, Oolakan, sand lance. Um, they're all the kind of foundation of the diets of so many species. So it's very important data. This, I guess one of the ongoing challenges as a modeler is the scale.
Yeah.
So with certainly with sand lance and with herring, and I'm not as sure about surf smelt, but certainly with those two, there's fairly good coverage now of habitats that are feasibly, areas that are feasibly good habitat throughout the Strait of Georgia. If we have one pocket area, it's helpful, like one smaller area, but then you have basically confirmed presence or a confirmed area that's good. But the for when we choose to model at a domain, like a scale or size of an area like this, what we hope for is good coverage across the whole area. We can still deal with it and still make use of those data. And to your question about are they being used, I'm not the right person to at DFO to confirm it, but I do have a colleague that has worked on it for many years, and the recent publications I've been aware of that are uh, making use of all the data they can get their hands on with respect to Sandlance. That's the one I'm thinking of. And so that the result of the most recent paper on that topic I've seen has been a big step forward because we can see all the potential habitats within the strait that are suitable for sandlands and even get some idea of how those areas have changed over time or how the habitat has been reduced or moved.
That's
So yeah, it's
awesome.
certainly valuable data. And
Yeah.
the other last point I think I'd like to make is that I don't know that people out there collecting the samples that we used for the first model I talked about, like ocean temperature,
Mm.
they, back in 1985, they're out there collecting these data. They're putting it onto a logger or they're writing it on a notepad, and then it gets filed away. And it does get used. Eventually, somebody is going to find those data and use them, and they're going to make use of them.
I love that. It's never throw away the papers of the citizen scientists and I mean, really,
Mm.
I know a lot of older people that have been doing data collection for years and years, and I'm just like, those are troves of
Yeah.
information for this amazing technology to bring it all together, to then look at the past, to then predict and also plan for the future. Can I ask a couple more questions in here before I sort of circle back to that? Because I feel like the usefulness of the model for conservation is probably on the minds of most of the people in this room, but maybe we'll end with that. So we had, how do you ensure that the data you're using to feed the model is accurate and reliable, especially across borders and institutions? What does bias correction look like?
Yeah, so two questions. The accuracy and quality control applied to the data we use. I mean, there's no quick solution. It's very time consuming, and I personally spend months on it, full time. But like, I even had the benefit of picking up a data set that somebody else had already quality controlled. So there are many points at which, the quality or the accuracy of the data can drift. There could be miscalibration of equipment, but there also could just be misinterpretation or mislabeling of the units of measure. Those steps are done. They are carefully looked at, and we do the best we can to take the measurements and the observations and ensure that there are no major errors. Um, so yeah, no easy answer. Digital record keeping has improved, I think, generally the reduced the frequency of major errors. But yeah, I mean, there's so many steps in which we notice these issues. Like if I get a temperature reading over all the depths of the ocean, and that point is in the middle of Vancouver Island, basically just throw it away. It's
Right.
not, something's gone wrong somewhere. But
Yeah.
it doesn't, when you're talking about tens or hundreds of thousands of measurements, and the error rate that makes it through the quality control, I think it's very low. Uh, the other question was about what does bias correction look like? So we don't, in this model, we don't actually feed data into it. So the model is just running. It's just a run in the physics, and then you take the model output and you pair it up with an observation and you say, okay, let's just check. And we do that for all observations. And then we see how they're similar or different. Then there's a calibration step. So like if there's something that seems to be wrong, we can go and tweak some dials and knobs on the model. The bias correction that we did was more about like data that are far away from us. They're like temperature and salinity that's coming from not a buoy, but you can think of it that way. Like if there was a buoy at the open mouth of the Juan de Fuca and it had some sort of error on it, we would bias correct by saying, okay, we're telling the model that the temperature at the mouth of the Juan de Fuca is 10 degrees. But that's wrong. It's actually consistently wrong by 1 degree. So it's saying, hey, it's 10 degrees, but it's really 11 or 9. And we'll just correct it at its source. So essentially, that's what we did. And we did it as a test just to see if really that would be impacting the center of the Strait of Georgia, which is 400 kilometers, 600 kilometers away. So indeed, it did.
Fascinating. It's yeah, it's a lot of test and question and go back and look and reevaluate the yeah, it's really cool. I mean, like this presentation for the data geeks among us, like it's fascinating to see what you do, like how you work with it. Yeah. I okay, so we have a couple of other questions in here. I wanted to just quickly though get to the lack, so something we saw in the presentation yesterday on kelp and kelp restoration was that the Jervis and the seashell inlets heavily affected by climate change, warming,
Hmm.
and the kelp forests really impacted. So I was noticing in your presentation today too that, although seashell inlet's not in there,
Hmm.
Jervis was really red. And I wondered, Um,
Hmm.
well, I kind of wanted to just note that we're seeing the same thing, different conversation or different species, I guess, that we're focused on, but the same impacts of the warming, I think, and um, on the kelp and on,
Yeah, yeah.
yeah.
No, I was out to in the seashell area just yesterday, and a resident there was asking me about that exact same thing. He'd been stand-up paddleboarding for many years and noticed that there's no kelp forest, not in Seashell Inlet or Jervis Inlet, just along the coast. There's no kelp forest where there used to be. And on a very specific example like that, it's not an easy question to answer without actually getting in the water and looking back, through records to see. But certainly heat waves and extreme temperatures do affect kelp. Kelp have, depending on the species, have this niche. So they want to be in a certain current, like current speeds are important for the bigger kelp. We know that. And then they have a sensitivity to salinity and temperature and other factors too. So you can have physical environmental factors that affect kelp forest. Obviously, if you change those, it's not going to be good for kelp. On the other hand, there's ecosystem factors too. So if you remove, we know if you remove sea otters from the system, the urchins tend to just create a barrens eventually where these kelp forests were. So there's lots of things that locally could be happening. Um, yeah, and then these inland fjords, they're particularly, like I said, they if you reduce if you increase temperature, you increase the resistance to mixing. And these fjords have a sill at the outflow. So they become very shallow where the sediment builds up. And
Mm,
over time, what they'll do is they will essentially flush less. They will mix less,
yeah.
which can have a bunch of knock-on effects as well.
Yeah,
And
that
also,
it's like when you put in the breakwater and then it backfills with sediments and fills up and nothing flushes anymore in a marina. I mean, for
yep.
people who are thinking, and I mean, different people come to these conversations from different perspectives, but we see that Gibson's Marina, it's always like, oh, it's so gross in there now because it basically fills and doesn't flush anymore. And that I was really wondering about that, like fjords, like Howe Sound, for example, is really deep. So it
Hmm.
felt strange to see that it would be warming along the edges, but that's the sedimentation thing.
Yeah, yeah. So this we have regular square cells in these models. There are other modelers that are actually just getting to the point now with the technology to have a different style where you have like a mesh, basically very fine where a very fine resolution where it needs to be fine. And those are exciting to look at because they're very good for Howe Sound or nearshore areas or the fjords too.
Yeah. There was we're gonna really quickly, there was a question about 75% of the water in the Strait of Georgia enters from the Fraser River. I think you said 115 billion cubic meters per year. That's a
Hard to visualize.
massive, is that wrong? It's a huge
No,
number.
no, that's right. That's right.
Yeah. That's
Yeah.
so, and the question was just, I mean, the impacts of that on freshwater networks and influencing local conditions. How is that what makes the Georgia Strait in part so abundant?
Um, it's not something I say yes, absolutely, or no, not at all. I mean, I think absolutely it's a factor. Yeah. The huge influx of fresh water is makes it an estuary, makes it an estuarine kind of environment. But what's very unique is that it's actually fjord system too. So the Strait of Georgia is 400 meters plus deep at certain points, which is not characteristic of an estuary. But what does happen is that with all this fresh water being pushed into the system, it has to flow out eventually, and it actually creates some mixing, and it um, simply put, it basically helps with water exchange to the open ocean as well. So there's something called the estuarine circulation, and that's a conveyor belt of water that is in part, got to be in part why the area is so biodiverse.
Amazing. We are literally at 1 p.m. and I know you had a pretty hard stop at 1 p.m., Greg, and I pushed us to the limit. So I just want to thank you again so much for coming and talking to us and sharing. We always say, that we encourage people to take action and get involved, and whatever resources that we get from you, we will put up on our Sunshine Coast Ocean Festival Nemo Talk page that is specifically for your talk. So afterwards we'll follow up and we'll see if we can get any more resources or links to support your work. And just thank you so much for leading us through this fascinating project. And we hope that the government will use it to protect the marine environment, because that's what we are working hard to do on our side.
Mm. Well, thank you very much for having me, Suzanne.
Yeah.
Yeah,
Take care.
much appreciated. Bye for now.
Bye. And I'm just gonna sort of wrap up before we end the recording, just do the follow-up and promote the festival. Tomorrow's talk, Thursday, June 11th, noon to 1 p.m. We will be hosting, Councillor Benny Pierre of the Shishaf Nation, hearing a talk on Shishaf marine stewardship. So we're really excited about that. And tonight we have a live film screening of Salmon Secrets at 7 p.m. at the Sunshine Coast Arts Center. And we have Alexandra Morton zooming in after the film to talk with us about fish farms and wild salmon advocacy. So that's pretty special. We look forward to seeing everybody tonight, hopefully, and at the NEMO talks for the rest of the week. Once again, big thanks to our funders and supporters, and a huge shout out to you, Billy Carroll, our fabulous film programmer. Without you, this festival would be so much smaller and less interesting. So it's just, hands up to this beautiful team. And we'll see you at the movies.